We continue the series about reinforcement learning in animation. And last time we've seen how we could have a discrete state space and a discrete value function. This time we will see how we could have a continuous state space. Hi, I'm Jerome, and today's paper is the near optimal character animation with continuous control, a paper from 2007. As usual for that paper, what I would do is import all the libraries I need, and then I will import my character, I will import different meshes that I will display, and the targets and that kind of stuff. And this time, it's a bit different. Instead of importing just an animation coming from the LaFan, I already pre-sliced the animation, because the way this paper works, it expects to have a bunch of clips of animations that are represented this way. So you start at the crossing phase, then you get the contact, then you get the next crossing, and then the next contact, and the last crossing. And that is considered for them as one clip. You get the clip in, it goes from the first crossing to the middle crossing, and then the clip out is the other part. So I will need to have that information. So what I've done is that I've already picked a few animations that are needed, and I've already set up the proper timing of when is the crossing, when is the contact, and all that kind of stuff. So for instance, I've loaded all of those, and if I display the first animation I have, it is this one, and that's the animation I will be using and slicing as clips, but I've already pre-processed all the informations of when those contacts happen, right? So what I need to do is to build their motion model the same way as they've done it here, really splitting the clips with knowing if it's the left foot starts, when is the contact, and so on. And so what I have is this, I get a bunch of clips, all the informations were already in. So I know how many clips I have that start with the left foot, I know how many clips I have that start with the right foot. That's all the clip count I have, so I have 36 footsteps basically. And I will compute that as being a sets of animations, a sets of clips. So I get the quaternion and positions for each of my clips and the different timing. And so I have as many clip count as I have as many frames I have, the bone count and the quaternions and so on and so on. So now clip Q, clip P will be a bunch of clips animations. And so this is recomputing the root to realign every time all the clips to start at 0, 0, and that's the function to compute those clips. So really just taking the ranges that I've decided and cutting all the animations, copy pasting, and realigning everything every time. And that's what I'm doing here now. I have inside of all my clips informations, I get all the different clips, all the different timings for each of those clips. Now, what is interesting in this model is that they decided to work without any IK, any post-process. So they need to make sure that when you blend the clips together, you don't need to post-process it with the IKs. And the way they've done it is they decided to say, basically, every time you try to blend an animation, so that's a clip here, the A is a clip, so you get the A in, A out. You will have the contact points. So that's where we decide that we have the contact. And you basically align the two clips together at that contact time. So that's what you do here. If I need to blend between clip A to clip B, first thing you do is that you move clip B so the foot that is in contact would not move, and you realign the entire animations relative to that. So every time you will blend, basically you're sure that the foot that is in contact with the ground would not slide, because you move the entire animation relative to the contact positions. So what I will do is that I will compute all those contact positions depending on the timing. So I know in my timings when is the contact, and I compute the positions of my foot every time I have a contact. So that's what I'm doing here in this function. The way I do it is I take the ankle and the toe, and I project that on the ground, and that represents the orientation of the position and rotation of the foot and how I would want to align everything together. So now if I want to display all the different clips I have, I can see the different contact positions, and I see the clip motions that I have. And when I pass the animation, I don't have any more animation. So that represents one clip, and I can go and then can pick any other clips. That's another steps. Let's see if I get something a bit different. One other steps and all that kind of stuff. And I get every time the contact with the 2 feet, and so I will be able to blend that properly. So what we do is that we'll see how we could actually blend the animations together and see how it works. So what I have is I have a player, again, that's allow me to keep playing animations depending on the states I'm in. And a clip itself is this information. So it knows the clip ID I have, it knows which frame I'm actually playing. And then it will also know when I need to start playing, because if you see here, for instance, when I need to go from B to C, because of the contact happening only at the end, I only blend during this timing, and that's mean that I will only start to blend coming from this animation, this frame in out. But I might also, is there an example where you don't start at the beginning? But you might also not start at the beginning of in, depending on how you align everything. So that's track me when I need to start to play my animations, start to blend. That's tell me when I need to start to play the current animations. That says how many time, how long is the blend. So all of that is computed when I said, I have a clip and I want you to align to another clip. That's the align function, what it's doing. And then I get the tick to say, play one frame. And the player itself will always have one current clip that it's playing, and he will have the information of the next clip that he wants to play. He will make sure that he aligns them and then check if it needs to play or if it needs to blend and that kind of stuff. So that's what the player would do. When it ticks both and do the blending and everything that I need to do. So if I put that in use, what I will have is this. So I get the red skeleton is the current clip, the green skeleton is what I will play after, and I could let it play basically anything. So what I'm doing now is I just pick randomly any clip to play. It choose which was the next clip to play. You could see that it can always blend. So some blends are terrible, some blends are fairly good, depending on how lucky you are when you pick your next clip. But that's how the animations is perfectly able to blend. Let's restart it. Blend all those animations and make sure that your foot is never sliding. You don't need any post IK solver or anything. This is just playing animations and blending them together. Now, we've seen how basically that's how the motion based database is done. So it's a bunch of clips you could play, you could connect those clips together, you can blend them, and it works properly. Now we do need to decide how we want to control this and how we will be able to interact with the character, not picking any stuff randomly. And so in the control part, what we have, they have really big state space with a lot of different values and that kind of stuff. But basically what they says in the paper is that they regrouped everything here in the paper, but they've never treated the state space as being that massive thing that can do everything. They've just learned different controllers on different part of the state space and that kind of stuff. So that's what I would do also. I would simplify the paper and treat only one case and work from there. And the first thing I would do is, because if I jump a bit in advance, The traditional thing that you will have to make sure that is trying to see if the next animations you want to play is coherent physically. So is the animation close together? Is the velocity close? And that will be the cost of what they call the physics cost that you could see here. So that's the physics cost, is how much, is how good is the transition going from clip A to clip B? Is it good or bad? So that we could pre-compute, because computing it every time will be losing resources. What we could do is just compute in advance the cost of that transition for every possible transitions we can have. So this is what I will compute here. Basically what I'm doing is I'm taking one clip, I realign that clip to when the contact happens, and then I go through all the other clips and I align all the other clips. And when I do this, then I will start to compute the distances between every bones for all the frame during the blending. So that's give me basically the cost, how close both clips are in the trajectories for every bones during all the blends. So I pre-compute that cost, and so that's what the physics cost will be here, and that's the interesting stuff to compute for the physics cost. And I will let it pre-compute all of those informations for me. It does it for the 36 clips with all the 36 possibilities. And I will start to also pre-compute a bunch of other informations that are interesting in my case. And is to pre-compute what will be the next states as soon as I take one of the transitions. So if you look at the control, what you could see is that you get the function from being in one specific state and going into a different clips, and how you do compute the new states. So what is the states? I will not go through all of those variables in my case. I will only learn the one that I'm interested in. And C basically is the clip I'm playing. X and Z are the position of my character on the ground plane, and theta is the orientation of my character on the ground plane. And I will basically only work with those one. And that will represent a state space for me. That represents one state. So the clip, the X position, the Z positions, and the theta orientation. That represents a state. And then if you try to do a transition between X and going to a different clip, this is the formula that gives you to find the new state that will be. So X prime will be the new states, and the new states will be the new clip C prime, and then that will be X plus the cosinus theta of delta X, delta minus sinus theta of delta Z. And how do you compute delta X and delta Z and delta theta? It is the blending algorithm that gives you that information. So basically, all the stuff that I compute when I do clip A and align to clip B and detect how much time I have to blend, where is the contact and that kind of stuff, that's what gives me the delta X, the delta Z, and the delta theta. It's really depending on each clip and how you blend the clips together. So I can, at the same time, I'm aligning everything to compute the physics cost. I can use that information to compute the delta X, how much, because I've realigned clip A, and then I could check where clip B arrive. In X, Z, and theta. And so I pre-compute delta X, delta Z, and delta theta. So I have all the informations I can use. I get all the deltas, I get the physics costs. I can start to check and work with all the clips. Now, I would divide the physics cost by the mean. So I get something I don't get massive numbers. I get something that stays between 0 and 2, 3, depending. So it's all normalizing the physics cost. And the last thing I would do, I would say that I know that I have a bunch of clips that start with the left foot first, and I have a bunch of clips that start with the right foot first. And basically I make sure that the cost of playing the wrong foot is extremely high. Basically just making sure that I would never try to play a clip on the wrong foot. And that's how I'm doing it here. It's just I make a really big cost of going into the wrong clip. The paper was doing something different. The paper was basically saying that every clips could blend with every clips. And if it's a clip with the left foot that want to play and blend toward another clip with left foot, they were mirroring the clip. But I didn't want to make the video too complex, because you need to track which foot is in front. There is a lot of mathematics at the end where you will start to need to flip all the mathematics, because you are on the mirror and animations, that kind of stuff. And it was easier in my case to just say, don't deal with the mirroring, just make sure that we will never play the wrong animation. So that's what I've decided to do here. Just make sure that you don't go into the wrong clip. So I've computed all the physics cost, I've computed all my deltas. I can now show what happens if I just let the system always play the least expensive physics cost. So now it will always play the animations and pick the minimum costs for physics. And you could see now you get something fairly smooth. So that's the optimal trajectory that the system can take by just checking the physics cost between all the clips. And I do this just by saying that the next clip will be the minimum of the physics cost, the one that's the least value. Okay, so we know how to blend the animations. We have the physics cost and all the deltas. Now we could start to play with all those real states and start to control them. So the transition function, which is this one, in my case would be a bit different, just because in the paper they've took as a convention that the character, when you try to put it on the path like this, they put the character as to say that they will be aligned toward X and it will walk along the X-axis. And in my case, I'm used to work along Z, so my character is looking toward the Z-axis and is walking along the Z-axis. So I had to switch a bunch of stuff to turn all the mathematics to move along Z and not along X. And so my formulas are here. This is how I compute. So the same thing, except I've changed a bunch of stuff. And so that's my transition function. So what I have is I got my clip ID, I get X, Z, and theta. So clip ID, X, Z, theta, that's my state. That's X in the formula here. That's X in the formula here. And the next clip ID is C prime. And that will return the X prime. So it returns the next clip ID as X prime, Z prime, and theta prime, returning me the new state. How is the state represented? Basically, the character, I will always want it to walk along the Z-axis. So a state is always represented relative to the desired path I want to do. You can see that we never define the desired path in the informations. The only thing we define is where my character is. It could be placed anywhere on the plane, but that plane aims in the direction I want to walk. And basically, the theta represents how much your character is rotated relative to the desired path. So that's the theta. And then your x and z is how offset you are compared to the center of that plane, basically. And that's the state space. That's how it is represented in this case, right? So I get my transitions to be able to transition. And now what I want to do is that I will want to use as a first pass, the simple policy I could have is to go through a greedy policy. And so what I will have is that I will have a direction cost. So how good am I walking in the direction I want it? And basically what we says, we know that we says that we always want to walk forward, and then we align everything relative to that where that forward is. So what the direction cost will be is that I'll take my x and z, which is my current positions, my x prime, z primes, that will be my future positions. And the only thing I make sure that the motion itself, so that's what you have going from here to here, the direction of the motion has to be basically 0. The angle of that direction has to be aligned to my z-axis. I want it to walk forward. That's what the direction cost is about. What I would do is that, because I will have animations that have a small step, bigger steps, I'm also making sure that even if my motion is in the right direction, I want him to make sure that at least it does a step in the right direction. So that's what I'm doing here. I check the z prime where I will be, and if that doesn't make me at least 10 centimeters steps, I multiply my cost by 3. It's just to avoid that sometimes I will have really small steps, but are perfectly aligned. I will pick that one, and so I will have something that start to walk and then make a really small steps. So that's where I would want the cost to be bigger. Say, now I want you to make sure that you move forward, not only that you make a really small step forward. And what is the greedy policy? It just takes your states. And what I would do is that I compute the transitions for all the possible different transitions you could take. And from there, you start to compute, you try to find which one has the least cost in total. And the different cost will be what we have here. You get the state costs and you get the transition cost. The state cost, in my case, I would not use the second part. I would only use the first part, which is the derivation. I want to make sure that I'm not in the state that deviates from where I would want to go. So not only I want you to walk in the right directions, but being offset, walking nearly in the right direction will give you a penalty. So that's what the deviation would give you. Says, if you start to deviate from the trajectory, your costs start to grow, and that depends on how far you went. You get the physics cost, so that's the one we pre-computed. How well is the transition doing? And then you get the direction cost, is how good am I walking in the directions I want you to walk? And then you sum all of those costs and you pick the minimum cost possible. So let's do the direction greedy. Then I take my gamepad, and now I have this character. So the yellow arrow is where I ask the system to walk, and so the greedy algorithm will just always check for the next clip and only for one clip. It's like we had in the previous video. When you go for the greedy algorithm, you picked only the what gives you the smallest error possible. without taking future into account. And so it's not too bad, but see there it just flipped, and that's because the physics cost probably, I have a bunch of flipping animations that says the physics cost of not doing the full flip will be too high. And so as soon as it starts, unfortunately, to put the foot down into that flipping animations, it has to keep doing the flip. And that's where I have, in this case, the greedy algorithm makes really bad choices sometimes. It could keep going and do something fairly good as long as it doesn't pick that wrong clip by mistake. But that's the greedy algorithm. And then you could choose how much the physics matter, how much the direction matters, how much the deviation matters. Now, of course, we've learned the greedy algorithm, but what is interesting now is to see how to find the optimal policy. And to find the optimal policy, what we have to do is, again, try to figure out the cumulative cost of picking one clip relative to another one and what you will be able to do in the future. And so what we have is that you try to minimize the sum of all the future costs you will have. And in this case, it could be written, of course, as a recursive function again, saying that my value function for x will be equal to the cost of being in a specific state plus the cost of picking a specific transition plus the value functions of being into that next state, multiplied by a factor to make sure that you can converge. And then you usually put that factors around 0.9, 0.95, something like that. And the finding the minimal, the best policy is basically now you take the state cost and you take the minimum of all the possible transitions you can take, and basically it means that the best policy possible is to find the minimum of the transition cost plus the value functions. You could see that what happens is to find the best policy, the state cost is not important anymore. Only the value functions and the transition cost is important. And that's because the state cost itself now has been learned into the value functions. The value functions depend on the state cost plus the future costs, which means that the policy to find the best clip to play doesn't need to compute the state cost anymore. It's already integrated into the value functions. And that's what you would try to learn. Last time we've done it with the Bellman equations and recursive computations on the discrete value. We're not in a discrete world anymore. What we want to do will be to learn it on the continuous value functions. And that's how you will do it instead of learning it step by step. What we will have is we will have to approximate that and use a linear programming to solve the system. So what we have to do is basically what I will want to do is that I will want to learn for my value functions. I will try to maximize the value functions because it's a cost function. So what I want to do is that I want to make sure that the cost will be as high as possible. But we will set a bunch of constraints to that linear programming, and the constraint will say that my value function for specific x needs to be smaller than the state cost for x plus the transition cost plus the future costs. And so by doing so, what happens is that you try to grow the value functions as high as possible, but you limit the maximum size of it by the fact that it always needs to make sure that all the different value functions between them needs to be always smaller than the cost plus the next one. So that's because of this, you've basically turned that Bellman equation into a linear programming optimization. And that's defined the exact same properties as how we learned it the last time. Now, one of the issues is that the value functions x here is continuous. So x can be any value of x, any value of theta. So that value functions has really enormous number of possible variable. So we cannot learn it as is. We need to approximate the value functions. And how we will approximate the value functions, we will basically go and says, we would turn that value functions into a bunch of basis function, because we know that the cost will be fairly smooth along all the values. I mean, if my state is at x value 1 and I'm in value 1.1, I'm fairly close to it, and I don't expect to pick an animation completely different because I'm so close to it. So all those value functions will be fairly smooth. So I can approximate them with basis functions. And that's what we will do. We will turn the value function of x into a bunch of basis functions, and the basis functions that will be multiplied by coefficients. And what we will have to learn now is the coefficients for all the basis functions, and that's what we will learn and keep iterating on it. So I get all my basis functions. And so if I turn this problem of maximizing Vx with all those constraints, now those constraints become the basis functions of x multiplied by my coefficients needs to be smaller than the cost plus alpha, the next one. Now, basically, you could see that I have my basis functions on both sides. So it means that I have to take the right-hand side and put it on the left side. And so it gives me delta x minus alpha delta x prime. It needs to be smaller than the costs, which means that I can turn all of this together and do alpha x minus phi x minus alpha phi x prime for the coefficients, and then I can learn the coefficients now for this one. That's how you actually turn this problem into linear problem you could learn. So what I would do is that I will have my compute basis, and the only thing I need to track if I want to walk forward is how much I've deviated from the trajectory and how is my character rotated. That will impact where my clip will go, and that impact which animation I need to take. So that's the two bases I need to learn. And so I will compute those two bases. That give me 9 bases. It's all polynomial basis functions. So what does it mean? It means that I have a polynomial for x, so it's 1x x squared. I get a polynomial for theta, which is theta 1 theta and theta square. And then because I have two different polynomials to learn together, you basically need to do an outer product all of them. And so that's why you get 1x x squared theta x square, theta square x square. That gives you all the 9 bases that you're trying to learn at once. So it's what they represent here. They said that they have the polynomial. So the simple polynomial that want to run, that you want to learn. And in the case of just having the task of walking forward, that's what they said, that the polynomial of degree 2 for x and the polynomial of degree 2 for theta. So, and multiply together, that's mean the auto product to be able to learn all of those. And my optimal policy, now when I try to find which one of the animation I have to play, it's what they've defined here. That says that, if you remember, it's this one, the argmin. So what I do is that I take the transitions, and that gives me the physics costs, and I get the direction cost because both of them are part of the cost of the transitions. And that's it. And then I compute the basis functions of x prime and theta prime, where I would be multiplied by coefficients, and I sum the two. So multiply by alpha. So I get alpha plus my value functions evaluated at x prime. And I'll take the argmin of it. And that's how you take the best clip to play. So I get my compute basis, I get my optimal policy. And now how you actually really learn this. Normally, if you wanted to learn the value functions and grow the value functions and do this, one way to do it is to first you take a bunch of samples, because of course it's a continuous value function, so you cannot learn for all the different possibilities. You choose a bunch of examples scattered along all the state space. So that's what I'm doing here. I take a bunch of x positions between -2 and 2 meters, and I take the sample theta minus, so on 360s to rotate everything. And I create a bunch of samples of those. So I get, for each possible clip, I will have the clip, the x somewhere, and the theta somewhere, and that give me a bunch of samples. So that's what I have here. All the samples I would decide to use. So I have 900 different samples that I will learn from. And if you wanted to do this, usually you could pre-compute all the possible transitions between all the different states and put them all constrained at once and says, now try to maximize your value functions with all of those. Now, it doesn't mean that in my case, I will have a 900 by 900 constraint. That's a big heavy to learn. And what the paper decided to do is to do it iteratively. So what you do is that you start with a bunch of sets. You start with a set of transition. So basically you start with all the coefficients at 0. You go through all your samples and you ask what will be the optimal transition to take. Basically, in that first case, that would be the greedy transition. And that's the list of transitions you will have. That's the list of constraints you'll create. You learn the parameters and you reiterate. You re-ask the system for all your sample, what will be now the best transition to take. And it will be, of course, a set of different transitions. So your L grows, and you recompute all the different constraints, and you relearn the value functions, and you iterate until you converge to something that will not add new constraint, which is what I'm doing here. So I will start by saying that the first thing is saying that I want to maximize the value functions. So what I said is I take all the samples, compute the basis functions for all the sample, and that give me my max Vx. That's what I'm trying to maximize. So you minimize it because you subtract it because by default Linear programming will try to minimize. So if you try to maximize, you just need to flip the sign. So that gives me the Vx I try to maximize. And then I go through all my samples that I've generated, use the optimal policies with all the coefficients I computed, check which clip it would choose, and if that transition does not exist already, I'm adding that in the transition states, and then that gives me all the transitions I want to use. And then finally, you go through all those transitions and you start to build the big matrix of all the coefficients. So you build the matrix of all the constraints, this one. And so how you do it is that you compute the basis, put that on the left hand, compute the new basis for the future basis for the new theta, new x, new theta. You subtract it from the alpha. And on the right-hand side, you get the cost of taking the transition plus the derivation factor, because that's what I have here. Cost of the transition plus the cost of the states plus the cost of the transitions. That's the right-hand side. And that gives you the matrix of all the coefficients you try to learn and all the right-hand side values. What I do also is I'm adding all the sample also, but the inverse of them, just to make sure that basically this will means everything needs to be smaller than the cost. And I will do the opposite, say nothing can be smaller than 0. So that's why I do the minus here, just to make sure that I put a lower bound as a cost functions cannot be negative or cannot be, well, it cannot be negative. So making sure that everything is up to 0. And that's because when I would do the linear programming, I would put no bounds on the values. I would let him choose the coefficients the way he wants. And so I need to give him upper bound and lower bounds on everything he tries to learn. So he get the upper bound as maximum is the cost plus the future, and lower bound is 0. That's what you do here. There is one thing that I haven't showed you yet, is that when I do the coefficients, I do have 9 coefficients. That's what I said. But what the paper says is that you cannot learn a value functions that will represent all the clips plus all the bases. Again, that will grow the dimensionality of what you're trying to learn. Instead, it's that you will learn a different value functions for each clip. So each clip will have the value functions of if I'm in this clip, if you want to reach in this clip, and you reach in the futures with those values, x theta and x prime theta prime, that will be the cost of reaching me. So you will learn it for every clips. That's what they call tabulations. So the possibility to say that you will want to learn different values for each clip. So I will learn different value for each clip, but I will learn everything at the same time, because I need to make sure that the value learned for one clip is reflected in the values that the other clip point towards and that kind of stuff. So that's why I have, for every clip, I get the 9 bases. I compute the coefficients and I put it inside of my clip ID. I put the values for the compute bases and put the next clip ID. I get the minus equal alpha for the future basis and so on. So I'm learning all the clips at once, but each clips will have different values. And so you can see that it has 3000 constraints, and adding new constraint every time and learning them, and that's already gone. That's the power of having only 36 clips, I would say, and being a bit more in the future compared to the paper that would taking around 1 hour to do this. And if you want to see what we've just learned basically for the compute basis, this is, if I take the clip ID 3, this is the compute basis for it. So you see, that's my X. So from x to from -2 to 2 on the x-axis and minus pi to pi on the theta axis. You could see that basically what it tells you is that it will be really costly to arrive in the negative x with negative theta, and it's basically less expensive to be on the positive side and kind of stuff. So finds you the sweet spot of, see, it's not even 0, 0. The sweet spot is probably better to not be in 0, 0 in this case. So that's what the value functions, the future value functions will give you. And now what I could do, of course, is use exactly that. So what I will have is, again, the same control, and my optimal policy will use my coefficients, my future stuff. So I will use the same functions I use for learning. And I get my x and theta coming from my controllers, depending on where my character is. And now you could see that if I walk forward, I should never try to do that wrong flip anymore. And I have my control, which is what they call the near optimal control, because we've learned for the future into a continuous matter. You have a continuous functions, you get a continuous control for the character asking to walk in the right direction. And this is it for this paper. There is a lot of different value functions that they learn, different basis functions that they've used, but I wanted to make sure that the basics were understood, to show how you could learn a continuous value function and use a continuous value function instead of the discrete one. I hope you liked it, and see you next time.